Hi, how's it going? Let's see. Okay, so any questions on anything? Kiet is sick or something. He didn't say what he had, but he had to go to the hospital, so something kind of serious, I guess. But anyway, he's not going to do the help session this afternoon. So if you have problems, just email me and I can help you with it. And then if you need, we can set up a Zoom call, on the same link as the class and just work out whatever there's issues on things. The next week I want to go to this ACS meeting, so I'm going to try to pre-record the classes on the weekend and then post them before the week. So hopefully that'll be okay. Next week I'll be finishing chapter 11, and then we'll skip because we're running out of time, so we skip the other. So we have chapter 11. Chapter 12 is van der Waals equations for mixtures. So and then chapter 13 is chapter 13 is more complicated equations for mixtures. So these are kind of involved, and we won't be able to they're pretty involved. So chapter 12 and 13 are pretty involved, and they end up doing these uniquac, unifac, and RTL functions, right? And then some other SSCED and this acid-base models, kind of more elaborate models for solution mixing. So you kind of need 12 and 13 to do 14. So what we do is not worry about the details of those, but just kind of figure out how to use those equations. So we're doing vapor liquid right now, and this is liquid phase separation and liquid solid phase separation. So so basically this involves more. You can use more elaborate equations in the Margulis two parameter and things like that. So same idea, it's like activity coefficients, but it gets to be more involved, like how you calculate those group contribution and things. So beginning of next week, well, I'll go through finish chapter 11, and then at the beginning of next week, I'll zip through like 12 and 13, touching on the high points. Then we'll use those in 14. So you don't need to understand those, but be able to kind of know the functions. It's not that hard to use them. It's a little bit harder to kind of go through the understanding of them. So 14 is liquid phase separation, which is an important topic. And then we skip ahead to reactions, like more advanced than what we covered before for chemical reactions, which is chapter 17. And usually we run out of time there. If we have more time this year, we might have like 1 or 2 more days this year. So if we have time, I'm going to do like acid-base equilibria, because that seems to be pretty important to a lot of the co-op jobs, like concentrated sulfuric type things and how you do calculations for that. It's after 17. There's a bunch of chapters in the end that are pretty involved, and I'm just skipping kind of through those in a sense. But we'll cover 14 in entirety and 17 in entirety. Right, and then whatever else we can put in. Might be nothing, but we might be able to squeeze in a little bit of the acid-base things. So hopefully that's okay. I think that's pretty much covers the gamut of what you'll need to know before you take a class in separations. And it should be enough thermo to function, to do plant design and things like that. So that's kind of the goal here. All right, so I want to just quickly finish going through the example problems in the chapter, and then do these the old quizzes, which are basically under 11, and then it was like 2020, 2019, 2017, and 2016. They're all kind of the same thing. So you could, once you do one of them, you can kind of see how all of them work. The older ones are like do calculations by hand, and the newer ones are just use Excel. Like 2019, 2020, we'll just use Excel, and we'll just use Excel. So it'd be similar to 2019, 2020, or if you do 2017 with Excel, or 2016 with Excel, because they're done by hand here for 17 and 16. So that's the general picture of what's going on. We already did this 11.5. So 11.5 is just calculate the two parameter Margulis coefficients using these functions, right? He gives single experiment could be used effectively to get the two parameters, and then he gives a composition. So he gives this one composition on this phase diagram. He's given this composition, the one where all the curves cross, which is 0.66 something, 0.6369 x1. It's a propanol water mixture. So so you need the gammas, and the gammas are so you have this equation for activity coefficient, yi xi equals gamma I p sat over p. And then if you know yi and xi, and if you know p, and if you can calculate p sat, that just depends on temperature, then you can get the gamma, right? And then once you have the gamma, you can plug the gamma into this. You have gamma and x. You have the two gammas and two x's, and then you can just plug those in and get the A12 and A21. So here, here he's already calculated the gammas from another example, and then he's got the x's, and that's all you need. Is that you need the y also. Let's see. 11.2, 11.5. I guess you have to iterate for p in this. So you have p times y equals x I gamma I p sat, and the sum of p times y equals p. So you have like x1 gamma 1 p1 sat plus x2 gamma 2 p2 sat. And then you can vary. Let's see. So you have x. He gives you x. He gives you gamma, and you can calculate p. Do you know the t here? Mention technical values calculated. Let's see. He's got p set. He's got A12, A21. I just wants you to calculate. Let's see. So how did he get gamma? Gamma he already got in another problem. So he got it by a method like this, solving for P. If you know the pressure, then you can vary the temperature. This P sats depend on temperature by the Anton equation. So you can vary the temperature and then find the pressure to match some pressure that you know. And then at that point, you have the temperature of whatever it is, the dew point or the bubble point. So you do an iteration to do that. So I'll show you how to do that. But this example 5 is just to get the A12s. And then example 6 is use the parameters of 11.5. So you got the two A12s for two parameter Margulis, and then to predict the dew point pressure. So dew point, you're going from a vapor phase to a liquid. So you're just forming the liquid, and when you form the liquid, the sum of the x's has to equal 1. So that's the rule of dew point. Right? And then we have this thing, so we have that we can rearrange that to be for x, and then you know if you're doing a dew point, you know y's because you're coming from a vapor, so you know the vapors, you know the y's. So you have like X is Y times P. So Xi is Yi times P divided by gamma I P sat. P sat depends on the temperature, dew point temperature, and then gamma I is just going to be A12. I mean, if it's a single parameter, like gamma 1 is A12x2 squared, and if it's a two parameter, it's this messy equation involves x2 and x1, and these two, A21, A12 that we got from the other, from 11.5, we just got those. Right, so you can get, if you know the x's and we know the a's, then you can get the gammas. And then once you have the gammas, and you know the y is the input, then you just need to know the temperature to get the x's, under the condition that the sum of the x's has to be 1. That means the sum of this thing, sum of these things, the two of these things, if it's binary, has to sum to 1. So you can do that. You can vary the temperature to get that to be 1, or if you know the pressure, if you know this pressure, that's usually the case, you know the input pressure, then you can calculate the pressure is going to be YIP plus Y2P. So Y1P plus Y2P is P, like this thing. Then you just say that you're just going to sum, you're just going to solve for P's and this thing. It's going to be 1 over 1 over the Y gamma P sat plus Y gamma P sat equals P. And then you just iterate that thing with temperature until you find the right P. And then once you get that, then you can calculate the x's, because you have the T for the P sat to get the x's. So you can solve for the composition. So that you do in Excel. So you go to, like, I have 11.6 here somewhere. Let me find that. Chapter 11, example problems. I think this is posted on the web page, but so you did 11.3 already, 11.6 up here. So this is an iteration, right? So initially, when you do this iteration, because gamma is involved, gamma depends on x. So you need to guess gamma first because you don't have x. So you're trying to get x, but gamma depends on x. Like in the one parameter Margulis, gamma 1 is x2 squared. So you need x to get gamma, but you don't have x, you can't get gamma. So the first thing you say is if it follows Raoult's law, then gamma is 1, because y, the k ratio, y by x, is p sat by p for Raoult's law. So gamma is 1. Right, so your first guess, you don't have x initial, so you just leave that blank. Then the A12s are fixed numbers you got in the previous problem. And the gamma you say is 1 for the first time through. For the next time through, you're going to calculate gamma. But if x is 0, so this is, sorry, this is, this I didn't write, I always do that, but this is ln of gamma. So it means gamma 1 equals exponential of A12 x2 squared. So if x2 is 0, and exponential of 0 is 1, so gamma 1 is 1. So this gamma equation works like D3 and 4, so 4 is exponential of D4. So that thing is going to be, if D4 is 0, this thing's 1, so that gives 1 for gamma. Anyway, that's Raoult's law, right? So it's kind of the assumption gamma 1 kind of assumes that x is 0 in a sense. But anyway, if you leave it blank, it takes it as 0. So it sets it to 1. And then once you have gamma, then you can calculate the y's, or the y's are known. That's the input. So you're trying to find the dew point, so you know the vapor composition. And then you calculate the p's, right? So you know so you want to compare like how the p is changing as you go through iterations until it solves the p isn't changing anymore. So that's kind of what the iteration is for. You do it until it stops changing. So the p is going to be 1 over p sat. So that's going to be this equation. So I'm going to have this equation. Okay, so it's going to be the sum. You're summing up here you're summing up 1 over P here. So it's going to be Y. It's going to be Y divided by P sat. So sum of the Y's by P sat. So this is Y by P sat, like Y1 P sat 1, Y2 P sat 2. Because if you get Y divided by P sat, that's going to be inverse of P, so you have to take the inverse of it. Right. So this thing will give you the P. Y by P sat gives you the P. Right. So the sum of those, inverse of the sum of those, that's given right here. See this equation 10(1), which is tiny. That's what you're doing, is sum of 10(1), which is, it's given in the problem statement. These things are given over here. Oh no, not that problem statement, and this problem statement. Sorry. So well, it's given in the quiz. I'll give you those equations, so you'll have that equation. I don't know in the, let's see if I have that in this quiz. The 2020 quiz is an example. So it gives you, like, here's the routine you have to do, and that equation is in here somewhere. Here, this equation, sum of Y over P's to get the P. Right, so first time through, the gamma is 1. So anyway, this is the equation you're using to get P, right? So then once you have P, you can calculate X. So X is going to depend on P. So here's P that you just calculated, right? That's 11, D11. So D11, P times Y, D8. So Y doesn't change, but you're iterating this, you're just using that cell of Y. And then Y times P sat, D11, or G, D6 times D6 is gamma times P sat, and then Y times P. So Y times P divided by gamma times P sat gives you X. That's here somewhere. And that's just our normal, this equation, right? Like X, so you can rearrange this, X equals Y times P divided by gamma times P sat. And so that's just that equation to get X. And then do the same for the other X, or the other X is 1 minus the first X. Then once you have that X, you can calculate gamma using this 2-parameter Margulis equation, this thing, right, that we had before. And that's just a definition of it. And then once you have the gammas, then you can calculate the pressure, doing that sum again. And then once you do the sum, so you'll get a different answer. Like that's this one, right? That has P sat times gamma, because previously it was 1 times gamma. Right, so it changed. And then because P changed, then when you calculate X again, so this X will depend on the previous one. So all you do at that point is copy the cell over and over again. Like copy these things by 2 and then put the thing down. And then it's already referenced back. Right, so you can just, that's and normally in a program you do an iteration, like a loop, but here you can just do a loop that way. You can see the 50, the final pressure is 50, so it's not changing eventually. It's just 50.6, right? It doesn't change. So you can do it a few times to get it to really not change, but basically it stops changing. You get 50.61. Then at that point, you know the pressure of the system, and using the pressure, you can calculate the X. So that's the X you're trying to get, the dew point composition and the dew point pressure. That solves that problem. That solves this problem. You wanted to get the dew point pressure in the liquid composition. Right, so that's how you do it, is just kind of iteration. So you have to practice doing that. There'll be a question like that on the quiz. And then that's 11.6. 11.7. 11.7 is a solver routine to get the rest of this we already went through. Benzene and ethanol has an azeotrope, right? So that's a point where that's a point like this, where it's a point where you get stuck if you're trying to do a distillation, like x to y, 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 and finally you can't distill anymore because y equals x at the azeotrope. So at the azeotrope, you have y equals x. And then if you have like this equation, oops, you have this equation, and that equation equals 1, right? Because y equals x. And you can say that like, then gamma equals p over p sat. Right? Like a gamma ratio will be just the p sat ratio. 1, 2 will be 2, 1. Right, so you have, that's basically the azeotrope is simpler. Once you have the azeotrope, like if you want to use that complicated the two-parameter Margulis model at the azeotrope, let's see. Yeah, at the azeotrope, you can use this also. So you can get the gammas and A12s at the azeotrope, that's all. It's just that this equation becomes simpler, like the x and y are equal. So that becomes 1. So the gamma equation is simpler. Right, so this is an azeotrope of benzene and ethanol, and it gives the pressure, the temperature, and the composition. So you only need one composition because the vapor and the liquid are the same. So if you just have one number, you can get the ethanol. One might says benzene, and then it's the same for the vapor and the liquid. So you just need one number to define the whole thing. And then use the two-parameter Margulis. So you can once you have that, you can get the Margulis coefficient. Okay, and that's not going to change. So the Margulis doesn't change. It changes with temperature, but it doesn't change with pressure, and it doesn't change with composition. Right, so it's just that A12 is just going to be proportional to 1 over T. That's it. Right, so if you run it at the same temperature, then you can change the pressure and you can change the composition and just have the same A12. So once you're given the azeotrope conditions, you can get A12. Once you have A12, you can go to any composition by changing the x's to get the gammas. And then once you have the gammas, you can solve for the compositions using this equation, right? Using the y and x that aren't equal. Right? And you can get the gammas by changing the y and x and the x and the Margulis coefficient equation. So what here, you're given that, and you want to solve these two A12 numbers, and then you want to calculate the composition of the vapor in equilibrium with the equimolar liquid. So you have to figure out what that means. Okay, so you have in this case a vapor in
If your safety is at risk, ask me to call emergency service.
That was Siri. Siri's got some kind of problem. Okay, so you want vapor in equilibrium with a liquid, right? So it means you have a liquid, and then you want to make a vapor. So that's a bubble point. So I'm not sure how to tell you how to figure that out, but basically, you want the vapor that's in equilibrium with a liquid. It means you have a liquid. You're making a vapor, and that's the bubble point. Right? It's just in equilibrium. So the bubble point, because you're making a vapor, the sum of the y's has to equal 1. And the thing you're making has to be like that because you have the x's. You already have the x's. That's the x's is the composition you're starting with. Equimolar liquid solutions, equimolar that your x's are 0.5. So if you look at this Margulis two-parameter guy, not that one. If you look at this one, if the x's are 0.5, so this is the gamma one here, then it's kind of strange because so you have x1 is 0.5 times 2 is 1. You have A12 minus A12 is 0. So you just have A12, 2, you have, and then 0.5 times 2 is 1. So you have A21 times x2 squared for gamma 1. And then gamma 2 is x1 squared times A21. See, it kind of isn't, if you're looking at the 50% composition, the equation simplifies quite a bit. But we don't exactly use that here, but it's true. So the 50% composition is like easier to calculate, it should be. That's the composition where we are. So so from that you can calculate, first you can use the Anton equation, the temperature, calculate, so he's given the temperature at 68.24, so you can calculate the saturated pressures and they're not going to change. Let's see, calculate the composition of the vapor in equal Equimolar liquid at 760 given the following Anton constants. So the let's see, the temperature does change here because the temperature, you're trying to find the dew point temperature. I mean the bubble point temperature. Right, so the temperature changes. So Psat is going to be a function of temperature. And then it's kind of the activity coefficient can be calculated. So then it gets the A12 calculated. The two parameter Margulis, the two parameters, the composition 50%. So you can get the gammas from the gamma equation using 50%. Then you want to find the bubble temperature for that. So he's got these methods, like this is for the bubble temperature. Right? So basically it's like using, so I'll show you how to do it in Excel. It's kind of easier to just look at it. This is 11.7. So let's see, 11.7's here. So you have X1, these are given, then the temperature, and then the Psat, that's the Anton equation. And so you have the two Psats and then the gamma, right? The gamma, this is that long gamma equation, this one that's shrunken here. It's this equation. That's the two parameter Margulis gamma, right? And then you can get both of the gammas from that equation. And those things depend on the composition, the X composition and the A12 and A21. So those are fixed, right? At that temperature, those are fixed. Let's see, no, these things depend on the temperature, right? So you're going to have, let's see, those two depend on the temperature. Temperature is fixed here. Let's see if I do this right. I think I did this right. So we got those two, and then the A12s we got previously, those were calculated from the parameters. And the Y here is the Y is the pressure 760, and then the top is X. So D1 is X times gamma D6 times Psat D4. Right. So those are the two Y's that you get. That's just the same equation we've been using. And then this is the sum has to equal 1. So you're going to, in order to get that to work, you need to vary the temperature to get that to work. So you just use solver to do that. So solver is just set up that you vary the temperature. So you're going to sum to get that to equal 1. So the sum of Y has to be 1 and get it by varying the temperature. So that's kind of simple to do. Okay, it ends up 68.3, and then at that point you have the Y composition also. But you knew the X and you get the Y. So it's just a solver routine. You just plug in all the equations and then solve it. So the bubble point was this iterative routine, and then the dew point is this just a solver routine to do it. Right, and then that's that problem. Then, so basically he does it by hand here. You can do it by hand, but do it in Excel because it's going to be a lot easier. Then the other problem here is, what do you do if you have a big group of data points? So we have, like, for instance, so all these were solved the Margulis for one point, but you have all this data, right, that you've not used to match up this curve. So why can't you use, so you could get a 2-parameter Margulis for every point here, right? So how do you use a data set like that? So this one is to do this, and he's got a pre-programmed spreadsheet to do this called Gamma something. And you can do it. He's also got a MATLAB thing to do it. So basically, it's easier to use Excel, you know. So here's the data points. Like you have known data points like X and Y that are in this. So in this plot, like in other words, the liquid's at the top because it's pressure. Then this is the bubble point, the top line, and the dew points here. So the two are in equilibrium across a constant pressure. So an isobar, right? So the triangle and the square here are two pairs. So you have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You have about 20, 22 pairs. So you could tabulate those. I see you have X1 and Y1, experimental, right? And then you have X2's 1 minus X1. And then you can calculate Y1, right? So Y1 experiment, Y1 calculated. So for each one of them, you can do a calculation. So you have the X's, the gamma uses a 2-parameter Margulis model. So this is trying to solve for the 2 Margulis coefficients, A21 and A12 and A21, using the big data set. I mean, somewhat big data set. So it's got 24 points in it. Right? And at the limit, you have X0, X2's 1, then the Y's for that. So so you can calculate the gammas using the Margulis, that same Margulis 2-parameter equation. Right? And then if you have the gammas, then you can calculate, and you know the Y's, then you can calculate P. Right? So you can have P equals Y1 times P. So we have Y over X equals gamma P sat over P. So P sat 1 for the component 1. Then Y1 times P is gamma 1 P sat 1 over X1. Right, so we can calculate, if we sum these terms, we get P, because the sum of Y1, right? The sum of Y1P gives you P, because the Y is summed to 1. And then, so basically you can get gamma 1, you can get P, you can get X1, and then you can solve for P, and you know the actual P for the thing, right? By changing the A1 and A2 on this thing. So if you know all the inputs, you can calculate A1 and A2. Or you can change A1 and A2 until you get the final P to max experimental P. In other words, these on this chart, these are at a fixed P. So like this point and that point are X and Y, and they're at about 55 millimeters mercury. Right? We're calculating that to match 55 by changing A1 and A2 to get the thing to work. So then you have two numbers. You have the experimental pressure from the chart. You have the one you just calculated, which is going to be the sum of these X gamma P saturated numbers, like this, whatever that is. Y1 times P. So Y1 times P is X1 gamma 1 P sat. So that's what it's summing. And then you sum those. So basically, you want to have positive and negative deviations equally weighted, so you square the difference. So take the difference between those two and square it, and this is all positive. You can sum that up, and you want that to be the smallest difference you can get. So sometimes it's a big difference, sometimes it's a small difference. So like 55, 53 is a pretty big difference, but 66 and 66 are about the same, right? So So this difference like varies across this, but because it's squared, it's always positive. You sum that, this objective is just a sum of those. And you want to get that to be the least that it can be. So it's called the least squares method. So you use solver, you say for that cell, so for this target cell, which is a sum of the squared differences, I want that to be minimum. So it's click minimum by varying the A1, A2. And you just hit solve and it finds them. All right, so that's kind of the routine to get, it's basically a least squares fit. It is a least squares fit. It's doing it in Excel in a chart. Right, so that's kind of the routine that's in this. You can also do multiple variables. He tells how to do it in the chapter. But that's basically the stuff for the quiz. Like those are the problems. So I want to go through any questions on that. I want to go through old quizzes here as much as I can do. Old quizzes are, so this is one of them. So I'll just start with the first one, like the 2020. It's the same thing. This isn't the right one. 111-2020. Okay, so this is the right one. So this is ethanol water. Ethanol water. So it's a vacuum distillation of ethanol water, right? And there's some data for the given for it. So first it says get the one parameter Margulis coefficient. So basically this is all in it's all in an Excel sheet here somewhere. Can't anymore. This. Ethanol water sounds right. Okay, so Margulis one parameters. So there's a bunch of data. I gave the data in the quiz. So if you go into this quiz somewhere, I gave an Excel sheet with the data in it. So this is the answers, but I gave the gray ones, right, which is like the temperature, and then the X and Y numbers. So this would be a chart like the thing, just like this chart, like there's X and Y, instead of pressure, it's temperature. So it's at some kind of vacuum pressure, fixed pressure, and then it's the same chart, but with, so it's X and Y with temperature and the Y-axis, right? So that's that. And then you need to calculate all this other stuff. Right? Put in equations for those. And the equations are kind of given here. Like it tells you how to do it more or less. So it's somewhat like following rules, but you kind of need to kind of have a handle on this before you start doing it, but maybe not. I mean, you might be able to just figure it out, but uses data to obtain one parameter, Margulis coefficient, by adding to the table the columns, blah, blah, and calculating da, 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 da. And then, so do the minimization I just showed you, like doing that minimization. So that's done here. So the P sets are that Margulis equation. So it's a, we had, let's see here. So we have like A12 for the Margulis times x2 squared is ln of gamma 1. So gamma 1 equals exponential of x2 squared times A12. So A12s are variable here. We need to get the gamma. So we're gonna guess A12 first and get the gamma, right? And we have the x2. And then we can get gamma 2 the same way. It'll be x1 squared. Right, so it's a one parameter, so it's symmetric. So that's what this is. 10 to the, I guess that's base 10. I guess this is log. It says base 10. Oh, no. This is for PSAT. Sorry, it isn't base 10. This is log, right? So this is just the Anton equation to get the saturated pressure. Then here, this is where you get the exponential of x2 squared times a12. F11 is a A12 number, adjustable parameter, F11, right? And then, so you get the two gammas. Then once you have the gammas, you calculate the pressure, P calc, right? And then the actual pressure is 190. So I calculate, I do the actual pressure minus that calculated pressure. And then this thing is the x is, so it's the x values, x times p sat. So E15 times C15, and then G15 is gamma. So it's gamma p sat x. That would be y1 times p. If you sum those, you get, so you sum that with y2 times p, then you get p. So that's the p calculated. That's the same thing we just did. This is just the difference between the actual p and the p calculated. And then once you have p, you can calculate y. So that's, well, y is going to be x times gamma times p sat divided by x, right? And then that'll give you y, or divided by p, sorry. X gamma p sat divided by p gives y. So then you have y calculated. Then you can plot like xy data, which is, I'm not sure which, it's like the blue and the yellow are x and y versus composition and temperatures on the y-axis. Then the gray ones are the ones that are calculated, the same x, but then the new y, right? And it agrees kind of okay. So the azeotrope for this is kind of right here. And then this part, because of the scatter in the data, you can't really see that it switches. In other words, you have the liquid to the left and the vapor to the right, and here the liquid's to the right and the vapors to the left. But you can't really see it because it's scattered so much. But you can't calculate an azeotrope with this data. Anyway, so you just use solver here to minimize this, right? You're going to minimize the sum of the squares. So sum of the squares, minimize it. So that box, and then by changing the single Margulis parameter, that guy. So that was done, and that's kind of the first part of this. So then that's A and B actually. A is just do the calculation, add those to the table. B is like minimize it. Then C, then you have the Margulis coefficient from that operation. So you can calculate the dew pressure at a certain temperature, right? So the dew pressure operations given here somewhere. Bubble. So these are in the back of the book, these charts. So the dew pressure is this routine. So in dew pressure, you're trying to condense a liquid, right? So you have to get sum of x. So in that case, you have a vapor and you're trying to make droplets. So the sum of the x has to equal 1. That's the idea for dew pressure, dew point, temperature and pressure. If you know the temperature, you try to get the pressure, right? And you know y over x equals gamma p sat over p. So for whichever component, right? So you're trying to get the x1, so you have, and you know the y1, so it's y1p divided by gamma 1 p sat 1 equals x1. So that's the thing you want. So you need to, and you're trying to find the bubble pressure, so that thing's an unknown, that pressure. And you know the temperature, so p sat's temperature gives you p sat from the Anton equation. And then gamma you get from, gamma is going to be A12, so gamma 1 is A12 times x2 squared. So gamma depends on x. So this is an iteration. So because to get x, and you're trying to get sum of x equals 1, so you need to know, or you know the t. So you need x to get gamma, you need gamma to get p. right? And you got the rule that you're looking at sum of x is 1. So basically, just sum of x equals 1 is the same as p equals this over this thing, right? So basically, you need to guess first. So you guess first gamma is 1. This is the thing we already did. You say Raoult's law, gamma is 1, you get x. Then once you have x, you can get this sum of p thing. You find the p, and you use that p to get x. And then once you have, because you need this equation to get x, has p in it. And then once you have x, then you recalculate, get gamma, and then gamma used to get p, to just loop this thing around, right? So that means you're gonna have to do that routine with this. So due pressure is gonna be that repeated routine thing. Right, so I made it a little bit simpler here. I made it in a line instead of column. So x1, x2 first round. Remember, I had those set to 0, so it's still set to 0. Then the gammas are just set to 1 here. And then the pressure from that arrangement is 60. Then the next gamma, this guy, the x is calculated using p. Using p and gamma gives x. By x is going to be y, which you know, p, gamma, and then p sat. P sat, you know. So it calculates p sat using the Anton equation here. There's the Anton equation. That's the Anton constant. So it calculates these two. Those are fixed because the temperature is fixed. You're changing the p. So p sat doesn't depend on p, right? And then once you do the first one, then they're all just the same. So just copy those cells and paste and paste and paste and paste until nothing changes. Like particularly the p doesn't change. And once the p doesn't change, the x doesn't change, then you have your dew point. You have the composition of liquid and the temperature or the pressure. You can do the same thing with temperature, right? So if you knew the pressure and you want to find the temperature, then you do almost the same thing. Right, so this finally iterates to the values, and at some point it stops changing and you're happy with it. That's good. I could have actually done that in 4 steps. So you can do this by hand, but basically it's easier to do it here and there's less mistakes if you just copy and paste each of the things. I mean, it's going to be much easier than doing it by hand. So that's the dew point part of this. Then so calculate the dew point pressure. Okay, does an azeotrope exist? So at 50 degrees for the system, use the Margulis model. So this is written out here. So this is the equation for x. So you want to find where x1 equals y1. So when x1 equals y1, you say that p is p sat. So because this equation, so you have this equation. So when x equals y, that equals 1, and then just that the p has to equal gamma 1 p sat 1. That also has to equal gamma 2 p sat 2. Right, so this is the condition for the azeotrope. And gamma 1 is exponential x2 squared a12. That's kind of from the Margulis model. And then p sat 1 by p sat 2 is gamma 2 over gamma 1. So you can rewrite that exponential x2 minus x1 squared a12 using this equation. So x2, so if you have x2 equals 1 minus x1, then x2 squared equals 1 minus 2x1 plus x1 squared. If you have x2 squared minus x1 squared, which is what we have here, then this x1 squared goes away. Let's see. One of these goes away. End up, let's see. So you have x2 squared. Actually, I have minus x1 squared, and then this is x2 squared. So you have 1 minus 2x1 plus x1 squared. So this part that goes away, then you just have 1 minus 2x1. So this thing's written wrong. It should be 1 minus 2x1. A2 gives p sat 1 over p sat 2. That means you can solve for x1 here. Solve for x1 just because you know the p sats, and then you know a12, so you can solve for x1. So that's done over here somewhere. This is part D, azeotrope. So where is that done? X1. So that's rearranging that equation gives this log equation by 2. That's the same as this equation. So it uses the 2 p sats. So it's using the p sats and then a12 to get the x1. Right, so you have x1. Then once you have x1, you can calculate y1, and if those two are equal, you found an azeotrope. Right, so you have x1, and then you can calculate p by this summation thing, the summation of the so let's see, finding p out of this. Someplace I did p. P is just gamma 1 p1 set, or if you do it, you can also do it by the sum of the y's. So let's see, how did I do it here? This is the x's. So you're using the x's to get the p. So it's like x1 and then 1 minus x1, x1 times gamma times p sat, and the sum of those gives p. In other words, x1 gamma 1 p sat 1 plus x2 gamma 2 p sat 2. So these are from this equation x2. This is y 1p plus y2p. So that thing goes p. Right, so you can calculate p from the x's and the gammas, and then once you use the x's and the gammas, then you can calculate y. Y is going to be x times gamma times p sat, x gamma p sat, right, for the two components, and then that gives you y, or for the one component, that gives you y, and that y that you calculated equals the x that you started with. So yes, it is an azeotrope. That's kind of the answer here. So that's that part, and the other part E is just make the plot of the numbers from this, plot the y and the x, and that's the plot I showed you before. That's the last part of this. So that's quiz 2, one of the quizzes. The others, that's actually a hard one of the quizzes, right? So but it's not a bad one to do. That one's a pretty good example. The others are similar, so this should be similar to the homework problems, and it's kind of the same thing. Oops, this is the next chapter, 2019. So these, that's not it. 2019 out of 11, sorry. This one looks more complicated. They're all the same thing though. It's ammonia water. It's showing you a evaporation refrigerator, right? Where you can use sunlight to generate ammonia vapor, and then it absorbs into water. It's an absorption refrigerator. Then when it evaporates, it cools, right? So basically, you can run a refrigerator on sunlight. That's the idea of it. So it's given just 1 point: pressure, temperature, composition, get the 2 parameter Margulis coefficients. So we kind of said how to do that already. Then also get the 1 parameter Margulis coefficients, and then use this Redlich-Keister model, which relates kind of the 1 parameter to the 2 parameter, and get these terms like B12 would be basically the 1 parameter model, and C12 would be the deviation. So you can compare the two and see how they act. So that's explained here. There's an answer in here, but basically that's just fiddling around. Then use that to calculate the bubble pressure. So this is the same problem, like D is the same problem. And then use it to get the dew pressure. So these D and E are the same thing that we did in the other quiz and in the example problems. Right, so it's kind of the same thing over and over. It's just some framed differently a little bit, and let you see what an absorption refrigerator looks like. Then the other one, the other quiz, I don't have time to go through this one. But it's the same thing, you know, it's the same as the other. And then 2017, it's actually the same system. It's ammonia water, and then but it's for this Catlin cycle cooling thing, Kalina cycle, ammonia water for power generation at low temperatures. But the problem's the same thing. Calculate the Margulis. This one has calculate the acid base Margulis, which is just use this equation to get the A12, and then calculate the bubble pressure, calculate the dew pressure. It's the same thing. Right, so they're all kind of the same thing. Wait, hopefully you can do that. I think it shouldn't be too bad. If you have problems, like email me, or you can ask now, but basically you can email if you have problems. I can work through it if you need help. Before or after the quiz, you know, or during the quiz. Okay, so we're out of time. So if there's any questions or anything, I'll stick around a little bit.